We left off. Oh, at universal hashing. If a malicious adversary chooses the key to be hashed for some fixed hash function, then he can choose n keys that all hash the same slot, reaching an average retrieval time of all of n. Since they all belong to a single slot, then it would be a linked list. Any fixed hash function is vulnerable to such terrible worst case scenario. So the effective way to improve the situation is simply doing a randomly choosing hash function that is independent of the keys and actually going to be stored. This is called universal hashing. It can yield probably good performance on average no matter which keys the adversary chooses. In universal hashing, at the beginning of the execution, we select the hash function at random from a carefully designed class of functions. As in the case of quicksort, randomization guarantees that no single input will always evoke worst case behavior. Because we randomly set the hash function, the algorithm can behave differently on each execution, even for the same input, guaranteeing good average case performance for any input. Returning the example of a compiler symbol table, we find that the programmer's choice of identifiers cannot now cause consistently poor hashing performance. Poor performance only occurs when the compiler chooses a random hash function that causes a set of identifiers to hash poorly. Does that make sense? It's based on using this input of randomly choosing a hash function. It's not based on the programmer's choice, but simply just the compiler's choice of the random function. But the probability of this situation occurring is small, which is why we really don't worry about it. Let H be a finite collection of hash functions that map to a given universe of U. Such a collection is said to be universal if for each pair of distinct keys, K and L in this case, in the universe of U, such a collection is said to be universal if each pair is this. Does that make sense? Let's read that again. Such a collection is said to be universal. Each pair in K of L in the universe of U, the number of hash functions H in large H, for which H of K is equal to H of L, is at most H absolute value over M. And M represents the total range the keys can represent, which makes kind of sense. With a hash function randomly choosing H, the chance of collision between distinct keys K and L is no more than the chance of this. If H and K were H of K and H of L were randomly independently chosen from a set, that would be the probability. The following theorem shows the universal class of hash functions and gives a good average case behavior. Note that Ni denotes the length of the linked list Ti. So this is theorem 11.3. Suppose the hash function H is chosen randomly from a universal collection and has been used to hash n keys in the table, the T, size n. Using chaining to resolve collisions, linked lists, if key K is not in the table, then the expected length E of n of HK of the list, of that list K hashes, is at most the load factor, which is alpha of n over m, since there is an average of n linked nodes in each slot. Thus, then, the expected length is E of n of k, containing at most 1 plus alpha. We do 1 plus alpha since we include 1 being the hash function and actually creating the key or getting the key being part of this all of n time. So again, prove the expectations here are over choice for the choice of the hash function and do not depend on any assumptions or distribution of the key. Okay. For each pair K and L of distinct keys, define the indicator rating variable. Okay, we define a random variable since by definition universal collection of hash functions is a single pair of keys which collide with the probability. At most of this, we have this being that probability. Therefore, by lemma 5.1, we have E being in terms E given x of KL has a probability of less than or equal to 1 over n. So let's revisit lemma 5.1. Actually, it might be faster if I just search in here, lemma 5.1. It's here. So lemma 5.1 is used everywhere. Let's actually find it on page 139. We're right now on page 260. We'll come back. We did this, right? We did this already. So we're actually on page 266. We'll come back. Okay, lemma 5.1 on page, yeah. Given a sample space S and an event A in the sample space, let x of A equal to the I of set A. Then E of x of A equal to PR of A. Shall be honest, I don't know what this means. So I'll revisit and explain it to you next time. That is page 118. Write that in our lists. Okay, let's go to 266 again. We'll just go back to the proof later. We'll skip that for now. Okay, and we can corollary. We can do the corollary. Let's try at least. Using universal hashing, the collision resolution by chaining an initially empty slots with M takes expected O of n time to insert n of n inserts, search and delete, containing m insert operation. Interesting. Since the number of insertations is O of m, we have n equal to O of m. So the alpha of O of 1. So we know insert and delete always take constant time, theorem 111.3. For each search operation is O of 1 with universal hashing. So by linear area expectation, therefore, expected time for the entire sequence of n operations is O of n. Each operation takes O of 1 time, or omega of 1 time. Not sure what that means. And theta of n bounds follow. Wait, do you know what omega means in computer science?
Like big O, like omega notation, like omega n.
Like, we know you have O of n, but like, what is omega?
Omega O of n is like upper bound on like how much time it takes for a program to run, right? Omega n is lower bound.
Oh, so this is lower down. I see. This is lower.
And the one with like omega, not omega, like
Oh,
circle
and
with
then
line in the middle.
that's
That's the
theta.
exact. If you know the exact running time.
Wait, that's exact or is that the space? Okay.
I forgot that name, but it's cool.
Wait, it's like this, right?
Big O, yeah.
Is this thing?
Yeah, yeah, that's like exact one.
Well, I don't know if it's exact. Is it?
Yeah,
Okay. I thought theta was always space. Okay, whatever it means. Let's come back. Look at terminology. Okay. Designing a universal class of hash functions. It's quite easily to actually design a universal class because we just use some random stuff that the computer already gives us. And you can use chapter, I think this is a lot of math, so I'll come back to this. 267. Says we should know set theory to do. 267. Next, let's do open addressing. In open addressing, all elements occupy the hash table itself. That is, each table entry contains either an element of the dynamic set or nil. So it has either an on or off set. And while searching for an element, we systematically examine table slots until either we find the desired element or have ascertained the element is not in the table. You know, Hadi Abdul also got Columbia likely.
Yeah, I heard today actually.
It was insane. Wait, do you think?
What is he doing major? I forgot.
I think medicine. I'm not sure actually. Should I ask Ankit to join our opening party?
Opening. Actually, I don't know if I'm gonna join, bro.
Why? I'm gonna be in class anyway.
Oh. So if the party host is not in the party, then what kind of party is?
Exactly. Wait, I'm gonna open at 8. That's okay. Wait, that means everyone would have been opened at that time, so everyone's gonna be free.
Skip class ended.
No, I'm not gonna do that. Because then, if I don't get it, I'll be like, well, I skipped class and I didn't get it.
No, then just take a nap. That's what I did after MIT.
Yeah, but I can't necessarily take a nap at 8 p.m. It is what it is.
Will you not take a nap right now?
I guess. Wait, okay, wait. You were telling me that.